Tell me what you guys are building at Novi.
We are primarily focusing moving edge processing on board satellite platforms. You find the needles on a real-time basis on board, and you just send those down quickly or cheaply.
My gosh, you have to analyze in space and send small bits of data. And what Novi discovered was, in solving the latency issue, you sort of crush the economic issue, the cost issue. And then there was a realization, my goodness, if we've crushed the economic issue, let's just roll it out into the commercial space.
This week, my guests are Amit Mehra and Michael Bartholomews. They are the co-founders of Novi, a space-based edge compute company. But wait, what is edge computing and why does this matter for satellites? Well, before we answer that, let's take a look at the conventional approach, a centralized computing model. This is a model where the data must be transmitted to remote data centers for processing and generation of useful insights. Downlinking vast amounts of data, however, is extremely time-consuming, expensive, and requires infrastructure to be built and maintained. Let's illustrate this process with a jigsaw puzzle. Our primary goal is to determine the final picture that is created by completing the puzzle. In a centralized computing model, we first need to ship every piece of the puzzle across the ocean, assemble the pieces, and analyze the image. Only then is the final picture revealed to the user. This method is slow and inefficient because of the time it takes to ship all of the puzzle pieces. Today, most satellites follow this approach. They send vast amounts of raw data to data centers back on Earth for analysis and generation of insights. Now imagine solving that puzzle directly on the satellite itself. Instead of hauling all of that data down, the satellite solves the puzzle and beams down only the answer. This is the value of an edge computing model. All the data processing happens close to the source of the data, and this is exactly what Novi wants to do: apply edge computing technologies to satellites in space. This matters when quick decisions count. Imagine a firefighter tracking a fast-moving wildfire instead of waiting for a long chain of data downloads and processing steps. The firefighter could get near-instant answers about the spread of the fire directly from a satellite overhead. Or consider a farmer monitoring crops across vast fields. They could receive targeted updates without needing to spend their time combing through countless images. In today's episode, we'll explore why Novi believes this shift is worth making. We'll look at how edge computing can shape both government and commercial operations, and what their low-cost multi-sensor VistaSat constellation could mean for everyone who uses Earth observation data. I hope you enjoy this episode with Novi. Now onto the conversation with Michael and Amit to learn how they're moving satellite computing closer to the action. Okay, Michael and Amit, welcome to the Just Rocket Science show. Tell me what you guys are building at Novi.
Anu, great to be on the podcast. Thank you for having both of us. We are primarily focusing on moving edge processing on board satellite platforms to lead the shift from what we see today, which is a large amount of imagery or raw sensor information, to more of a actionable intelligence model. So if you are able to, on the collection platform itself, quickly generate a small amount of highly processed information that the end user actually cares about. And if you're able to send that very quickly and very cheaply to where it needs to go, that essentially transforms how space data is used today. And we feel that is a key requirement for proliferated use of space data, which really hasn't happened thus far. So that in a snapshot is what we're trying to do.
I want to break down the technology stack as we go through this episode. Let's start by defining edge computing at like a very high level.
Yeah, so the idea is obviously you move the processing as close to the sensor, right? So for us, there are 3 or 4 elements of the full solution. The first one is the actual OBC, the onboard computer. So you need a low power, low form factor processor that can operate in the space environment, namely deal with radiation, thermal environment, vibration, shock, all of that. So there is very much a hardware component that basically shifts the processor on board the satellite platform itself. The second element is what is the algorithm or the software that you are running on that. That can range from detection, segmentation, classification models that look at an image, process it real time, and extract a feature of interest. It could be state of health monitoring algorithms, autonomy algorithms, certainly in the domain of space domain awareness, looking sidewards, being able to classify objects of interest. So you name it, but if you have the processing power, you can run a very large number of quote unquote models or AI software on your OBC. The third element is the actual platform, the satellite. So we focus on multi-sensor satellites. And then to wrap it up really quick, the last element is it doesn't help you if you have process intelligence, but if you cannot send it quickly to where it needs to go. So we use a comm channel that allows us to quickly get information there. So those are the four elements that we think of when integrated. They allow you to produce low cost, low latency intelligence.
So it's the computer, the algorithm, the satellite, the communication stack that you have to address in this whole picture. Okay, so Michael, in your time during, say, the shuttle program, what did you see to be the need for services like these, even 20, 30 years ago?
My goodness, I think you're now asking me to date myself here, Anu. So I think I think back in those days we were just focused on getting the ships up. So this really wasn't Earth observation wasn't much in my purview, 2.5, 3 decades ago. But I think it more recently became just abundantly clear to me that there was an opportunity here, right? I mean, you see the usual suspects, whether it's agriculture, forestry, maritime. There are a lot of these areas that could benefit from Earth observation. But I think the thing that always struck me was just the expense associated with. And, if you look at the users are looking at buying economy cars, looking at buying Fords and Chevys. And today's purveyors of data are trying to sell Ferraris and Lamborghinis. And so there's this mismatch between people providing this useful data and those who can afford to purchase it and leverage it. And so I think this was an awareness that became more and more evident to me in the last 5-10 years, especially in my forays in fields like precision agriculture and mining and materials. I saw the tremendous benefit for this type of data, but it just never fit sort of budget and wallet. So this was a more recent awareness for me, Anu, and especially based in sort of the different commercial realms I've participated in. I think companies have been incrementally trying to drive costs down, but it's not sufficient, right? Most companies today will subsidize commercial business based on DoD business, and to do that, you can't reduce the cost down by 2x or 3x, right? I come from part of my career was in the consumer electronics industry. You need to put Moore's law in space. You've got to reduce costs down by 1, 2, or more orders of magnitude. And that is really what Novi is doing, is setting up a swarm of satellites, low-cost satellites in space that provide multi-sensors on there and provide low-cost intelligence that provides insights that are 2 orders of magnitude cheaper than available today. By so doing, you make the economic model wash and you democratize the usefulness of this data.
You've outlined some of the financial challenges really well of democratizing data and making data low cost. Are there other challenges with edge computing in space?
I think the bigger problem has been, how do you create a compelling enough value proposition to drive enough customer engagement and use cases, right? I mean, today's space data is limited to obviously state agencies and a handful of enterprises that can afford expensive imagery, right? But very similar to what the iPhone did terrestrially, when that platform, which at the end of the day is nothing more than a set of sensors, it's got a camera, it's got an accelerometer, a keyboard, etc. When that platform became available to the wider developer community, you saw what happened with quote unquote the app revolution, right? So again, what we are trying to do is open up access to the space-based platform, the space-based infrastructure layer where developers have an idea of the type of sensors they can access. They have an idea of the process and guardrails as to what they need to do to develop software for this platform. And then you really open it up where it's the power of many that hopefully allows new applications and new use cases to blossom, right? That's sort of been what's missing.
You'd want a way to easily get your data out there to the world, get users interested in your data so they know that the data exists.
Yeah, certainly. So, what we're setting up, Anu, and we've already set this up. Our commercial constellation. We will start deploying our commercial constellation at the end of next year and going into 26. And we've got our DoD asset going up in the next month or so. But our commercial constellation starts to get deployed at the end of next year. What we've done as a prelude is we have set up a platform, and it's essentially where developers can go in there. It's a simulator, and they can use archive data and start to get comfortable with the process of uploading algorithms, getting insights back. So it's a simulator before they get behind the joystick. And so initially, we're going to start developing a set of beta users who can then really become evangelists and become our front runners in propagating this marketplace. And this platform is actually a marketplace. So if you're an enterprise, you can go into your particular portal to upload your algorithms and get your insights, or we can write the algorithms for you. If you're a developer, you can develop the apps, and then users can purchase the apps. So it's really a private public marketplace for the broader enterprise and developer community. And this then becomes, as you can imagine, that becomes an organic process. You get your initial beachhead developers and enterprises, the word gets out, and this starts to develop, certainly with a high quotient of marketing on our end.
Got it. Tell me at a high level, how is, say, the processor different from typical computer processor, other than radiation hardening, perhaps?
I would say, just like you try and engineer any process for the specific use case, right? I mean, the boards for a laptop are very different from the boards for a server, which are very different from the chips that run on your smartphones, which is very different from the chips that run in a Tesla car, right? This is, again, one of those use cases that has its own set of specific requirements to which you have to tailor the product. But I would not say, there's something extremely show-stopping or something that is huge leap for this environment. I think it's a matter of time before processing moves on board. What we're saying is not, rocket science. I think the world knows that you have to move processing on board the platform, and you're already seeing a number of entities that are starting to onboard it on the platforms, right? We think Maxar's, some of their new satellites have processing on board. Planet is starting to move in that direction. A lot of the SDA tranches obviously need some level of processing. And then there are a bunch of providers that are coming in. So I think this is a big market. There is room for multiple players. And it's really, what is your value proposition? For us, we are trying to strike that balance between performance and cost in a manner, where if we have TRL 9, we can start to get some first mover advantage in that space.
Yeah, and I wanted to ask you, what is latch up?
Okay, so I'm probably gonna butcher this because, like I said, I'm not an electronics guy. But when you have a single event, so radiation, again, from my high level understanding, you have total ionization dose, which is just what you're seeing over time, and most parts are rated up to a certain threshold, right? The other one is if you have a single event, there's a solar flare or some level of cosmic rays that provide a burst of energy that typically messes up your memory chips and your processors, right? So there is a way to clear those using software-based techniques and bitstream scrubbing and things like that. But there are also destructive latch ups where, if you have an event, you are not able to recycle the boards. So while TID is somewhat easier to deal with, my understanding is for latch up immune or to deal with single event failures, it is more intrinsic to the manufacturing process and the silicon. So you do get chips like, for example, the AMD Versal is rated for the single event failures versus some of the other ones that are not able to deal with those types of failures. So for all the electronics peoples out there, I apologize if I messed up the reasoning, but this is my best understanding of what happens.
Essentially, it's a bit flip in space where some bit flips are recoverable, but some bit flips are not recoverable. You mentioned the AMD Versal a few times, and I'm very excited to talk about those products. Let's start with the SP120, which was your flight proven product. What was its key offering?
The SP120 was designed with the Xilinx UltraScale. We had an NVIDIA GPU. So what we were doing there is, for the first time in a compact form factor, offer FPGA processing, ARM-based processing, and GPU-based processing, right? So you can think of a couple of use cases. You can certainly use redundant processors to do the same task. What we were doing is we were doing very fast detection on the FPGA, and then we were doing the more difficult segmentation / classification on the purpose-built GPU, right? The AMD platform, I believe now, has its version of what's called AI engine, so sort of the equivalent of GPUs. But again, we would like to offer the flexibility of the main processor, the FPGA, and sort of these AI engines. Again, in a compact form factor, we tend to design the OBC to be both software and sensor agnostic. So what I mean by that is, it's a basic core. We have an SDK that tells people what they need to do to run their software on our processor. We certainly want to open it up and be algorithm agnostic. The other thing is we have a flexible interface board that allows us to made up with a variety of sensors, a number of subsystems in the bus to act as the flight computer. But if someone wants a unique interface, it's a very easy flip for us to change the interface board and not mess with the main board. So that's the part where we try and get sensor agnostic and algorithm agnostic, generic high compute in a low swap space factor.
And is that what happened with the SP240, where you improved the processor capabilities by moving to the AMD Versal chip?
Exactly. So the biggest difference was the Xilinx is not rated for single event latch-up, right? We were able to get good TID performance. And again, we do have rad-hard power supplies. We have a rad-hard supervisor that manages the main processor, and a variety of other ways to deal with radiation-based failure. But if your core processor is not rated to single event failure, you do have a weak link. So the AMD Versal provides that single event immunity, and it is a better processor by way of capability and power requirements. So it was definitely a step up in a much more compact form factor.
Okay, understood. I was very excited when you mentioned your beta program, and this, I believe, is for VistaSat. Can you tell me a little more about this program and your flagship offering here?
So as Michael said, we are trying to fold time in a little bit where, until our first two commercial assets go up at the end of next year, we are trying to see if we can work out all the elements of the customer pipeline, right? So again, to paraphrase his words, can we get you behind the flight sim before you actually go into the cockpit? And what that means is if you are a customer, say you have a use case, right? I'm a construction company and I want to get an idea of what wetlands look like in a certain area, right? So far, I have not used any kind of space imagery, right? I've generally always had boots on the ground, and it's been a fairly labor-intensive offering. Can I go into your platform? I can see what models you guys offer in your marketplace, right? They might be an existing land use or a wetlands detection model or something else, or I can contract you guys or a third-party developer to put that model together, right? I can go in, I can request, look, this is the area of interest. right? We can source imagery from all the existing providers. We can run the model on our backend emulator. So you get an idea of, what the performance on our OBC is, and then you start to get the results. So you really go through the entire pipeline using existing elements such that, you're not waiting for our data to come in. Instead, when our data becomes available, it's an addition or a drop-in replacement to the existing sources, which again, thanks to people like Planet and others, are very well developed, right? So can we leverage existing data sources to really flesh out the rest of the pipeline? That's what we're trying to do with that platform.
What is the key differentiator then when your real-time data comes in with the edge computing system on board? What is the next step up that users get?
I think really what happens when our live data comes on board is it just becomes a lot more affordable, Anu. So I think initially our beta users, there's a cost implicit on using archived data and generally available data. As we transition to our own constellation, then we drive costs down very dramatically. And maybe it's worthwhile, Anu, just to provide just one example to give you a sense of the cost equation here. Today, let's just say there is an interested party, whether it's a logistics firm, a hedge fund, that wants to count backlog of ships in Baltimore Harbor, and they want an annual report. They want to look at this. Well, to source the data from a Planet or a Maxa and then analyze it through a geospatial insight or whatever the case may be, an annual price tag for that is about $150,000. With Novi's solution, you're really that the cost, now not including Novi's margin, would be about $700. So that is really what we want to exercise our beta users into, is preparing them for sort of this brand new world of a completely different cost structure and economic model.
And to clarify, the $700 is not much for a hedge fund, right?
It's not much for a farmer, which is why this becomes ubiquitous, right? It's when you look at, and that's, when you look at that, this is, you have to match the value of the data, has to match the ability to afford that data. That's really what we're doing here. I think another point I'd like to make, Anu, and sorry if I digress a little bit, but part of what needs to be solved with the current state of affairs today is you have a variety of constellations. Some may have multispectral images, others may have optical, some might have RF. And so you've got to synchronize sources of data from multiple constellations. And these different constellations are maybe they address certain elements or certain parts of the problem. What we are trying to do is really be very, very purposeful. We have a smaller satellite, low-cost satellite, that'll have 4 sensors. It'll have optical, hyperspectral, IR, and RF. So we can look at the world and listen to the world in a very, very sort of data-rich type environment, and then synthesize the data that is useful and in a very low-cost manner, transmit it to the people who care. And we believe it takes this, it's sort of a disruptive approach, right? You can bolt on computers to a constellation to do something. You may need hyperspectral data. You may need optical data. All companies providing this have already taken in hundreds of millions of dollars, and their cost, their depreciation doesn't support a low cost structure. We're really trying to disrupt that. Low cost swarm of satellites, revisit rate, once a day, multiple sensors that are synchronous, and then you provide low cost data. We believe that's what it takes to make Earth observation a very user-friendly and affordable solution.
Yeah, this is a great idea from a commercial perspective. I 100% agree. What's been the demand like from a government or a defense perspective?
Yeah, so I think we have to differentiate between 2 big market segments, right? I would say half the world, which is DoD, anything that's safety critical, fire detection, things like that, is not driven by cost sensitivity. They are driven by latency, right? So half the world cares about getting intelligence very quickly in a matter of seconds, right? I don't want to wait for an image to get downloaded during the next ground pass and to analyze it on the ground to tell me what the configuration of aircraft on an airfield is, right? I want to know immediately, 6 aircraft, and all I care about is the number 6 versus petabytes of imagery, right? And I want it very quickly. So half the world cares about latency. The other half, which is the commercial world, does not need information in seconds, minutes, or even hours, because it's not a dynamically evolving situation, right? If I'm a farmer looking for what the hydration level in my field is, it's fine if I get that information over a period of days. I don't need it in a matter of seconds, right? But Michael's point, what I care about is it has to be 2 or 3 orders of magnitude lower in cost. And again, this is not rocket science, right? If you are sending bytes of information versus terabytes of information down a narrow bandwidth, expensive pipe, you are going to greatly reduce the cost, right? So that's what we're trying to do. So again, I think the demand drivers are very different for these two markets. On the commercial side, I think if you reduce the cost, we've seen some pretty good signals. But some part of it, honestly, is very similar to when the iPhone was introduced in 2003 or 2004. No one really foresaw what would happen. I think there's a little bit of this here as well, which is if you can really bring the cost down, how much does that platform play open up the market? So I think a little bit of that is still to be seen.
Anu, maybe I can just bolt on to that. It's interesting because this sort of relates to the genesis story of Novi. It's very indicative of a lot of disruptive players in other industries, right? Novi working for the DoD specifically was addressing latency. And latency meant, my gosh, you had to analyze in space and send small bits of data. And what Novi discovered was, in solving the latency issue, you sort of crush the economic issue, the cost issue. And then there was a realization, my goodness, if we've crushed the economic issue, let's just roll it out into the commercial space. So when you look at it, even though the different verticals have different value, latency or economics differently, our genesis was addressing latency, which then by default addressed the economic aspect of it.
Yeah, I certainly hear you guys on the latency and why the government cares so much about that. I mean, in the 2020s, we saw a war play out in real time between Russia and Ukraine, right? With satellite imagery, the whole world knew that there was a war that was about to break out because of the incredible amount of geospatial imagery that came in real time very quickly. Are there any other learnings that you took from the government perspective to the commercial perspective?
I think one element of DoD use cases is a little bit of the multi-domain environment. So, let's say your space layer sees something, it triggers an air layer, maybe a ground layer, right? So the parallels here, could be, again, if I'm a farmer and I want to get an idea of what part of my field needs fertilizer or hydration, right? Today, the model is I buy an image for $1,000, have somebody figure out what areas need servicing and go do it, right? Could you almost automate the process where if in space you have perimeter lat long for what is an area of interest, that directly gets transferred to your connected, John Deere equipment or whatever, and it goes and does the activity. I think, we're starting small with the space domain, but one can foresee in the future links to multiple other elements where you can make the process much more automated, reduce costs further. So I think that could be one area of, parallel learning where for very different reasons, you are able to connect additional domains and complete more of the full solution.
I think in that example, Anu, Amit hit the nail on the head, right? We've been talking to analytical firms in the precision agriculture space. And this is particularly relevant when you have these large remote farms, right? You have a lot of remote agriculture. And so if you can get intelligence from space that triggers a drone or triggers an on-ground hydration system, you really now integrate this intelligence into IoT on the ground, and you start to develop a highly accurate, low-cost, nimble system that can have a tremendous impact on boosting productivity and land management. So Amit is right. I think that was one of the learnings that we are taking, is sort of this multi-domain translation from defense into some industries. In a really weird way, agriculture is probably one of the nearest neighbors to defense. It really is, when you look at like asset management and productivity and efficiency.
Does the data transmission layer ever seem to be a concern where we can't transfer, gigabytes of data a second down? Does that matter with edge computing?
So the whole point is to eliminate that, right? You're sending down petabytes or terabytes to use the needle in the haystack, right? The model today is, if you're looking for a needle in the haystack, we send the entire haystack down, we discard 99% of the hay, and we find the needles on the ground, right? Which obviously adds cost and latency. There is certainly a section of the market which does not need the hay. You find the needles on a real-time basis on board, and you just send those down quickly or cheaply, right? So yes, transmission is a fundamental barrier, and the only way you are going to get information direct to device or direct to the end user is if it is extremely small amounts of valuable information, right? That's kind of what we're going to. We are not targeting, and we are not looking to replace the established providers who do provide that raw data source, and there are plenty of applications where that is absolutely needed. We are trying to complement that capability instead.
I understand. So you want to be a complementary data set to all of these other services that are out there. Are there any other edge computing use cases that Novi plans on exploring in the future?
I think the next lateral move would be around, instead of pointing things downwards, do you point them sidewards for RPO and in-space type activities, right? So space domain awareness, at least from the DoD standpoint, is an increasingly important area of interest. For that, you need processing. Whether you're trying to map something out, whether you're trying to classify, what looks like panels, how big are there, what look like thrusters. So I think the next lateral move would be around SDA. There's a whole element of edge processing that happens for comm satellites. I think we're not necessarily heading in that direction, because most comm providers tend to do that with some level of hardware on board. So I would say SDA, space domain awareness, and elements of autonomy are the two other big areas where onboard processing comes in. So if you're doing, state of health monitoring, automatic fault detection, corrective actions, certainly as you start to look at potentially GPS denied environments, I think all forms of autonomy need processing. So those two are the next areas that we are starting to look at, but again, purely from a DoD standpoint.
All right, so I want to zoom out into the bigger picture a little bit. Novi wants to lead the transition to edge computing in space. What does ultimate success look like for the team in the next, say, 5 or 10 years?
As I mentioned, Danu, our constellation starts to deploy in about 12 to 15 months. And really success to us will be the adoption of this marketplace we're setting up, where we start to see a biodiversity of users, enterprises, and developers. And then, that marketplace starts to become a vibrant and growing asset that a broad swath of people use. To us, in the next 5 years, if we have that marketplace functioning, we've got this platform as a service model that's taken a hold and growing. That's what success looks like in the next 5 years.
Do you ever see a future with open data?
I think it depends, right? I mean, certainly you've got to completely separate your commercial assets from your DoD assets. You're not mixing those two. Within your commercial assets, again, it comes down to, I think, customer and data rights, right? Like who owns it, who does what. There's obviously a lot of people who feel proliferation needs open access. So that is true, right? I mean, you go back to Apple, there's that balance where if you have captive control of the entire system, you can optimize the experience, but at the same time, you have to open it up so it really proliferates. So I think there is a balance, right? I mean, to get on the App Store, you have to do a few things, but it is open to the world. I don't think it'll go completely in the direction of, fully open, but like I said, controlled access, but open access is probably how far things will go.
All right. Well, I'd like to close out the podcast with one of my favorite questions that I ask. And this question is about contrarian bets. So basically, contrarian bet is an idea that defies conventional wisdom in the industry. An example is SpaceX betting on making rockets reusable and the whole industry thinking it was impossible. So besides building Novi, what is a contrarian bet you guys are taking in the space industry?
So based on what came out of November 6th, right, or 5th, how much of the industry can we change to truly, do what SDA set out to do and what the Space Force set out to do, right? I mean, it has become a little bit of an addition to the legacy way of doing things versus, replacing the legacy way of doing things. It remains to be seen, I think, how much of what we do in aerospace as a country on the defense sector, which then permeates into the commercial side, how much of that changes in the next 2 or 4 years in an actionable manner is certainly one area of interest. I'm not sure if it's contrarian enough or if I'm addressing your question, but that's the obvious one that at least comes to my mind.
If I were to paraphrase what you're saying, I think you're saying that with the new administration, there will potentially be an increased adoption of what I call new space technologies,
right,
where entrepreneurs in the new space industry are taking these contrarian bets on new technologies. But historically, the government and the defense sector has been slow to adopt to those, either from a risk perspective or from a cost perspective. But now they have the incentive where a lot of these technologies are being lower cost and they're being proven out more quickly. So hopefully the adoption from their perspective will increase.
Right. And I mean, you are seeing it, right? I mean, the NGAs and the NROs and the NOAAs of the world are buying commercial data. So it's just a question of, it's been a slow ramp up. Can that really accelerate, and how much of that kicks in remains to be seen.
My contrarian bet, Anu, is laser focused on what Novi is doing, right? I mean, to me, that is sort of the contrarian bet, is just a purpose-built, low-cost constellation that'll drive Earth observation intelligence down by several orders of magnitude. That's contrarian enough for me.
Great. Awesome. Great answer. Well, we're right up at time. So thank you, Amit. Thank you, Michael, for being on the show. Very happy to have you on. And I hope to have you guys on again after your constellation is built and deployed.
Thank you. And thank you for hosting us, Anu. It's been a delight spending this hour.
Thanks for watching this episode. If you enjoyed the episode, make sure you hit like and subscribe to the podcast, and see you next time.